So this morning I noticed an interesting phenomenon while I was in the shower, which was that the shower seemed to levitate all by itself. The moment of the force of the water on the shower head was the same magnitude and in the opposite direction to the moment of the weight of the shower head about a pivot where my fingers were. The shower head seemed to hover all by itself. And I thought to myself, can I use this and some everyday equipment that you might have in your kitchen or in your toolbox, can I use this to find out what the speed is of the water as it comes out of the shower head? So I did some quick calculations to see if I could investigate this phenomenon. One of the first things I needed to know was what the weight of the shower head is. And the issue is that the shower head contains water as well. So I have to somehow weigh the shower head when it's got water in it. And I decided that I would weigh the shower head and the water separately. I weighed the shower head when it was empty, and then I filled the shower head with water, poured that into a measuring cylinder. I didn't have a measuring cylinder, I had a Pyrex jug, and I measured the weight of the water that was in the shower head. Adding those two together gave me the weight of the shower head and water. The empty shower head came in, well, at 175 grams. The empty jug came in at 532 grams. The weight of the water in the shower head plus the weight of the jug came in at 553 grams, 554 grams, 556 grams, 550, is there any more in there? I think that's it, 557 grams. So the total mass of water and shower head together was 175 grams, that's the shower head, 577 grams, that's everything together, the water and the jug, and 532 grams, which is the empty jug, minus plus. So 220 grams is the mass of the water and shower head together, which is, well, I'll put it in, equivalent of 0.22 kilograms. Multiply that by 9.81, gives us 2.1582 to five significant figures, 2.1582 newtons. We can assume that the 2.1582 newtons of force is acting at the centre of gravity, which we'll say is in the middle. So we need to know what the length is of this shower head. Using a tape measure, measuring from the end, I make that 21 centimetres, near enough. 21 centimetres. So at about 10.5 centimetres, we have 2.1582 newtons acting. This is how our picture currently looks, with our centre of mass being the point where the weight of the water and shower hose are acting. And we are assuming that the pivot is right at the end of the shower. It will be okay. Order of magnitude, maybe two significant figures, this should be okay for a calculation. We also need to know the distance from the pivot to the centre of the force that the water is applying to the shower head. So using my tape measure, I make that 17.5 centimetres, near enough. 17.5 centimetres. So I've added that distance to the diagram as well, and the force arrow pointing up. That'll be the force of the water on the shower head. Now, because the clockwise moment must equal in magnitude the anti-clockwise moment, if I do 10.5 centimetres, which is the distance to the centre of gravity, multiplied by the weight of the shower head and water, 10.5, enter 2.1582 times, that is the moment clockwise on our diagram. the moment anti-clockwise must equal the same thing because we were in an equilibrium. So if I divide that moment by 17.5 centimetres, missed the 1, 17.5 centimetres, then that will give us the force of the water on the end of the shower head. The force of the water is 1.29492 newtons. Now here's the clever part. This is Newton's second law. The force is proportional to the rate of change of momentum. If we assume the velocity of the water is constant, then the rate of mass flowing, or the change in mass per change in time, can be measured. The force divided by the rate of mass flow will give us the velocity of the water. So we have to measure how much mass flows and how long it takes to flow. We have to measure how much mass of water flows out of the shower in a certain amount of time. Now I programmed into my calculator a stopwatch. And although the numbers are a little bit clunky, in milliseconds, I think that'll be okay for what we're using it. Let's exit out of this. So I'm going to take my calculator, the jug, and the shower head back into the bathroom, and I'm going to time how long it takes to fill the jug. I'm going to fill the jug with half a litre of water, measure the mass of that water. Even though I can assume what the density of water is, I might as well measure it. And then divide that by the time it takes for the water to flow. Problem is, I'm now going to have to try to find a way to hold the jug and my calculator and my phone to record this all at the same time. And I've only got two hands. We'll see how I get on. 2.64 seconds. 2.64 seconds is how long that jug of water took to fill up. So I have my jug of water here, and I'm going to measure the mass of the jug of water. Yes. 1.017 kilograms. So the mass of the water and the jug was 1.017 kilograms. And we're going to subtract from that the 0.532 kilograms of the jug, giving us a mass of 0.485 kilograms for half a litre. It could be that the volume calibration on the jug is a little bit off. It could be because it's warm water and so it's a little bit less dense, although I don't know how much impact that will have. Substituting numbers into our equation, we have the force that must be applied on the end of the shower, 1.29492 newtons. We have the mass of the water that flows in a time 2.64 seconds, which is 0.485 kilograms. And the one unknown is V. V is the velocity of the water. So rearranging that equation, 1.29492 newtons. Enter, multiply that by 2.64 seconds, and divide that by 0.485 kilograms. Gives us a velocity of the water of 7.0486 meters per second. So there you have it. If you've ever been curious how fast the water comes out of my shower for some reason, it comes out at 7 meters per second. Give or take quite a large margin of error.